Okay, looks like it's the top of the hour. Thank you everyone who is joining us. We have a few announcements as everyone joins today. First, we are recording this session and it will be available in Whova, our conference app, within 2 weeks after the conference ends. If you'd like to ask our speakers a question during this session, please use a Q&A area to the right of the screen. The chat window is where you can engage other attendees. And we kindly ask you to keep your microphones and cameras off during the presentations and follow the presenter's lead on when to engage with cameras and microphones on. It looks like we're ready to get started, and I'm going to hand it over to our speakers to let them begin. Kevin, over to you.
Thanks, Ryan. Welcome to our special session on some of the amazing advances in coupled fire atmospheric behavior modeling. We're here today to talk really about the application space. How do we use these new and developing tools and put them in the hands of managers in a way to be successful? And so I'm really thrilled that we've got an amazing lineup. But I do want to encourage everybody to take a look. I mean, because the Q&A is going to be a little clunky, just through the chat window. We do have scheduled for tomorrow morning at 11 o'clock a joint fire circle with the modeling group from yesterday, Alex Dye's special session. And so we're hopeful that we can have a really good conversation in a much more normal manner tomorrow at that fire circle. So please put that on your agendas and plan to attend if you don't get your questions answered in the chat. To start today, I'm pleased to introduce my friend and colleague, Dr. Rodman Linn from Los Alamos National Lab. He's going to give an overview on coupled fire atmospheric behavior modeling, some of the tools that are currently out there and some of their performance capabilities. So Rod, why don't you kick us start here? You're going to have to unmute though, Rod.
I have to get my window back. So can you hear me now?
Got you loud and clear.
All right, so I'm going to start by just saying, first of all, I'm presenting this work, but it's certainly not all things that I have done, and I'm happy to just kickstart this session trying to represent the full suite of things that we're going to talk about today. So first of all, I wanted to just say a little bit about what do we mean by coupled fire atmosphere models. So these are models that explicitly represent the atmospheric motion surrounding fire and the feedbacks between fire and the atmosphere at some scale. Now, these can be developed for a variety of different scales, everything from weather models, weather-driven scales, down to sub-meter scales. So this means that we can have fire models that are coupled to nested mesoscale atmospheric models, or models that have the capability to run down to centimeters. These tools are also developed for a variety of different applications, and the reason why they're probably most appropriate for different applications is because the developers have put focus on different pieces of their tools. So these can be everything from large-scale wildfire prediction to event reconstruction to prescribed fire planning, or even down to science investigations. And they all have different sweet spots. As with all modeling, it's really important to always keep in mind that these models are not appropriate for all applications, and it's important to understand their limitations that were associated with the foundations upon which they were built on. So I've now skipped. No, I'm good. Okay, so I just wanted to go through a few things here that these models can be used for, because they are connecting the fire to the atmosphere and the response of the atmosphere around them. They can be used to look at fundamental wildland fire behavior and the way the environment affects those fires. And so in this case, we've got a density current that runs across, this could be a thunderstorm outflow, for instance, that runs across the fire and changes the fire dynamics. And as you see here, the top image is an isosurface describing the position of that density current through a density contour. And the bottom is wind vectors in a plane. And you can see the way this rotor is affecting that fire spread in that lower image and stretching out that fire line, accelerating its spread, and driving it to go faster and more intensely. So here's another example where Janice Cohen has used a couple fire atmosphere model to simulate a portion of a car fire. And one of the things that Janice has repeatedly pointed out, and I think it's really important, is when we back up and try to validate these models, it's not just do we get the net rate of spread right, or do we get the area right? It's a multifaceted fire behavior that needs to be considered when we talk about validation and are we getting it right. We want to avoid getting it right for the wrong reasons and assuming that means the model is performing well. So another thing that we've just started doing, this is an effort that was actually led by Kevin, was to start using these models to do lessons learned and develop training ideas. Here was, again, focusing on a density current interacting with a fire and thinking about what happened in the Dude fire. In these images, you see 3 white dots in the different images, and those were the locations of burnovers. And thinking about how the density current might have driven that fire to accelerate and catch the people in those locations off guard is something that we can learn a lot about. And when we start using these couple fire atmosphere models, we're able to back up and focus on that. Carolyn Sieg has led a lot of work thinking about the interactions between multiple disturbances. In this case, we've got a scenario where Carolyn led a study where we had ponderosa pine forest mainly, and we were looking at the synergism between a bark beetle mortality event and fire behavior in those forests. And some really interesting things came out of here as we looked at the synergism. And synergism is defined as amplification of the fire behavior or the fire effect on the remaining forest after the bark beetle attack. Was that the synergism really was highest at the low wind cases and not so apparent at high wind. And that may not be, that's a little counterintuitive, or at least it was to me. But in this case, it's because at high wind, the influences of the bark beetle attack and the mortality, and here we have 3 different levels of mortality, the impacts don't really affect it because the fire is going to spread in an intense way without the bark beetle attack. And so it's really the low wind fire scenarios that bark beetle might impact the fire behavior most. And it, of course, is different when we go to scenarios where we have the gray stage. Some other work that's showing a lot of opportunities right now for this couple fire atmosphere tools is to think about exploring the strategies and trade-offs for proactive fire management. This could be the effectiveness of mechanical treatments on wildfire behavior. It could also be looking at the coupling between the ecologic and hydrologic process and looking at ecosystem sustainability or stability, or sustainability or stability. Thinking about how do different treatments or prescribed fires affect smoke and the trade-offs there, as well as doing landscape level planning. In the lower left, we see an image where just a cartoon where we can think about having high frequency prescribed fires, for instance, in the green line versus lower frequency wildfires, especially in the no hour long future as we go forward with climate change. Adam actually has led some work where he's connecting hydrologic and plant succession models with fire behavior models and tree injury models to look at how these successions affect the landscape as a whole. So it's important when we think about these coupled fire atmosphere models to keep in mind that there is a spectrum of different fires, and not all these fires are the same. Intense fires, for instance, they often have very strong drivers, whether those be winds or fuels or topography. And those contributing factors or those drivers are often at landscape scales. And that makes these fires fairly resilient to small scale heterogeneity or fuels or heterogeneity in the fuels or short-term lulls in the wind. If we walk down that spectrum to marginal fires, these often have a lack of strong drivers, right? We're typically not in strong winds, or we're not in heavy dry fuel loads, for instance. And so they're much more dependent on the localized conditions. And whether we be talking about winds or fuels, the heterogeneities or the transient behaviors become really important. And oftentimes it's actually the correlation between those transient wind events and when the fire is at a fuel gap, for instance, that matter in fire spread. So if we step back and now think about prescribed fires, which I view as a really, really important frontier for these tools, it's important to think about what are those characteristics of prescribed fires and the requirements for prescribed fire modeling. So prescribed fires are often performed in ways or locations that don't have strong drivers, or the strong drivers can be managed through the ignition patterns. They're purposefully designed to use such that the dynamic ignition patterns can influence the fire behavior and the smoke lift to get the objectives of the burn. And the multi-scale fire and fuels is a critical context for the way these fires burn. If we look at the movie playing in the upper right, each of those aerial ignitions is by itself a very benign fire. This is a very low wind, moderate fuels, but when you put them together, the context creates this ring fire as they burn together that has overwhelming impacts. And so one of the really important things that we need to be able to capture for prescribed fire is the interaction between multiple fires. So I just want to point out the difference between wildfire context and a prescribed fire context. On the left, we see a wildfire. And as that wildfire burns through this forest, it removes fuel behind the fire. What that does is it allows the wind to sweep in and drive the fire faster. On the left, we have three different horizontal slices of the same prescribed fire, where that prescribed fire is being lit using an aerial ignition moving from right to left, but the wind is moving from left to right. And so the context here is we're burning the fuel out, even if it's just mid-story, downwind of the fire. This creates a very different wind regime than we had in the wildfire, where the fuel is being removed upwind of the fire. And these kinds of things are important to keep in mind when we think about application of traditional wildfire models to prescribed fires. So I think we've gone through a lot of these already. So I just want to highlight, we really need to be able to think about how do these purposefully designed ignition patterns influence the way fires burn, the importance of the way multiple fires interact, and the influence of fuel heterogeneity and the transient winds around a fire.
We're on about 2 minutes.
That's fine, thank you. So here is an example of a fast-running tool designed for prescribed fire. What we're really looking for as we go forward with this kind of model is to make sure we're capturing those attributes that we had on the previous slide, and thinking about whether we're getting that appropriate interaction between the fires and whether or not we're getting the heterogeneous burn patterns that we would appropriately get. We need to continue to make sure that we've got the ability to do a variety of different ignition patterns and capture the effects Here I'm going to show a set of images where on the left I'm showing surface fuels and on the right the aerial fuels. These were a set of simulations supporting Nick Skoronsky and Mike Gallagher in the Spring Hill, New Jersey regime. It's important with these tools to be able to look at the influences of, for instance, decreasing the surface fuels or increasing the moisture and how that affects the burn and how it affects the consumption. It's also important to be able to play games with those ignition patterns. Here was a case where Mike and Nick and others said, well, let's look at what a ring fire does. Oftentimes they use ring fires when they want a high intensity fire, and it should change the way the fire burns. And so what we see here is a purposefully designed ignition pattern to where you get convergence on the safe zone upstream, and you see the fire convergence, and you're getting a much more complete burnout than you were in some of those previous movies. And the other thing that Mike and Nick suggested was that we look at some burn operations that they typically use, and they called this one a catcher's mitt, where we had spot fires that had spotted into a unit. And so they might do some ignition patterns to basically try to catch those spot fires. Unfortunately, the winds we were using in this case were variable. They were based on tower instrumentation. And it turned out that in this case, one of the ignition lines that was being lit to catch spot fires actually caused fire outside of the unit going forward. Being aware that that can happen is certainly something that we want to pop out of these models. And the simulations I want to leave you with, if I can get my slides to advance, are these simulations that were run by Daniel Rosales and Zach Cope based on some ignition data supplied by John Wallace for the HITCHY prescribed fire, for a HITCHY prescribed fire. In this case, we see a combination of black lining along roads and an aerial ignition and the complex burn pattern that shows up in this complex topography and heterogeneous vegetation. And so we really want to keep this in our sights as where we want to be for having tools that can be useful for prescribed fire planning and operations. And I'm going to leave it there.
Great, thank you, Rod. Good overview of really where we're at. I think it's an amazing time, you know, to be thinking about modeling of fire behavior because of the just dramatic expansion of tools available and their capabilities, and so that really is a wonderful overview. I don't see currently any questions in the chat, but if some of the other speakers have any questions for Rod, feel free to jump on in if you got the ability to unmute yourself. Great. While we're waiting for questions, Rod, if you want to go ahead and unshare your screen, we'll start the process of loading up Ruddy for the next speaker.
Sounds great.
Still time for one question if anybody wants to jump in. Awesome. Well, we'll go ahead and move on. It's really a privilege to have worked with Ruddy and Rod, you know, two of the most, you know, the world's foremost experts in coupled fire atmospheric behavior modeling. And Ruddy Mell is a combustion engineer at U.S. Forest Service out of the Pacific Northwest Research Station, and he's going to be giving our next talk on really what is, you know, has been a 15-year kind of labor of love developing the WFDS and FDS tool suite. And he's going to talk today about exploring trade-offs in computational speed and physical fidelity in coupled fire atmospheric modeling. And Ruddy, we'll go ahead and let you get started right away. And I'm sure there are going to be questions at the end of this talk, so we'll hopefully have.
Okay, thanks, Kevin. You guys can hear me fine? Everything's good? Okay, good morning. So I'd like to thank CERTUP, who partially funded this work. And this talk is covering our current state in terms of our exploring trade-offs, as Kevin said, between computational speed and the results of a model as you reduce the physical fidelity of the model. There's two model suites here. It's a little confusing. We have WFDS and FDS, and we're moving all the WFDS capabilities into FDS, but was not done sufficiently for this talk. So most of the results here are from WFDS, and it will be clear when we get to FDS, which is towards the end. So this slide provides a motivation for the use of these coupled fire atmosphere models by comparing a model with and without, two models, one with and one without coupled atmosphere, fire atmosphere interaction. So these are 1 hectare plots of a grass fire. On the left, you have a model that does not have coupled fire atmosphere interaction. And on the right, it does have that. The colored lines are time of arrival lines. They're separated by 20 seconds. So the further apart those are, the faster this fire has spread between those points. So on the left, you can see there's essentially a repetition of the same pattern between the red lines, which are ATV ignitions, and the ATVs start at the bottom of the plot and go towards the top at 3.5 miles an hour, or 1.6 meters per second. So you have a head fire spreading between the plots, or between the ATV lines from left to right, and then backfires from right to left. The simulation on the right has significantly different behavior. Between the first two ignition lines, you do have a head fire that covers most of the area between those ignition lines. But between the second two ignition lines, you have a head fire that's spreading towards the ambient wind. So in the opposite direction of all the other head fires you see. And this is because, of course, you've got the head fire upwind that's blocking all of the wind downwind of that. And also it's generating winds towards itself. And then the head fire that's downwind is also generating wind. So this whole interaction between the fire and the atmosphere is causing this marked difference between these two models. So in as much as this kind of behavior needs to be captured in prescribed burn planning, this demonstrates the need for these coupled fire atmosphere models. So in this presentation, we're going to have results from 5 different models. I'm not going to go into the details of these models. And I've listed them here in order of decreasing physical fidelity. So the first is what we call PB, or physics-based. And this is in this simulation only study, the kind of the gold standard that we're comparing the rest of the models, which are simpler in terms of physical fidelity. So that's what we compare to, because we don't have, well, it'd be great to have observations, and they're rolling in more and more with time. But for now, we're just a simulation only comparison. So then as we move down this list, we have what we call level set 4 and level set 5. Both of these do have coupled fire atmosphere interaction. And then the last 2 models do not have coupled fire atmosphere interaction. And I'll discuss that a little bit more later so you can understand better how to distinguish these two. The simplest model, which we, as I said, we call level set 1, is equivalent to Farsight if we use a Rothermel head fire spread rate for a surface fire. And we assume the local wind the local wind is equal to the ambient wind, so it's unchanging in space and time, which is what Farsight assumes. When we do this, we get agreement with Farsight, which you can see in this plot here. They're essentially, this is showing again time of arrival contours, and the models are essentially the same. So when we implement the level set approximation, we need the rate of spread for the head fire. And if we have that, and we make the assumption that an ignition at a point spreads as an ellipse, the fire perimeter spreading from a point ignition spreads as an ellipse with a fixed length to breadth ratio, we can use the rate of spread in this elliptical assumption to implement the level set model in a coupled or uncoupled from a computational fluid dynamics solver. These are assumptions that are commonly made. It's in Farsight and in other models, and we can do other things too and have the capability to do other things, but the results here are based on these kinds of assumptions and approaches. So how do we get this headfire spread rate? It can be from observation. It can be from an empirical formula. You may have a range you want to test. But if it is from an empirical formula, normally those formulas use the ambient wind speed to determine the rate of spread of the headfire. If we're using that formula and coupling it with a CFD model that gives you the local net winds from coupled fire atmosphere interaction, there will be an error because obviously the local winds are going to be different than the ambient winds that are unaffected by the fire. However, this may be good enough to investigate trends and do relative comparisons. And all models that currently that do have coupled fire atmosphere interaction and use a level set approach, such as WRF S-Fire, do have this error in it. But the consequences of that are still not really known. Lastly, in this list, we can get the headfire spread rate from the highest fidelity model, the physics-based model. And that will account then directly for the influence of the local wind as generated by the coupled fire atmosphere interaction. This does mean that there is some complication because that local wind may be influenced by the grid resolution. But as an example of how you can determine that headfire spread rate from physics-based simulations, we have this slide where on the left you see simulations of an Australian grassland fire, which is ignited from a 10-meter ignition line here, and then you have these different fire footprints every 25 seconds. And we ran a number of these simulations with 5 different ambient wind speeds and 4 different initial ignition lines, and we get this scatter plot of spread rates as a function of the local wind speed 2 meters above the ground. So we can fit this scatter plot with this polynomial and then use this formula in the level set coupled to the computational fluid dynamics solver. And that's how you get this plot here, which I showed earlier. This is from the level set 4 implementation, and the simplest case model over here on the left was a level set 1. So that 1 hectare plot is actually embedded in a larger area with a forest, so with understory and overstory, which I'm showing on the left here. And a plan view is on the right, where the black is the different the locations of the different overstory components, and the colored dots are showing the locations of 3 different types of understory. So I'm going to show a movie here of simulations of that scenario. They're from the physics-based, and then again the level set 4 on the right, physics-based on the left. You can see the physics-based, which has a much higher resolution, 25 centimeters horizontally and starting at 7.5 centimeters or 3 inches vertically. You can see it better resolves the circular structure of what we assume to be cone-shaped vegetation. On the right, where it's a much coarser grid, 1 meter, it's more blocky and rectangular. So as this fire progresses from the ignition line, you can see, as you know from the previous plots, a head fire forming here and here within the level set case. And you have consumption as the green unburned vegetation turns black. And here we have beginnings of an interaction of the head fire and the backfire. You can see the head fire is pretty well reproduced in terms of its spread rate and its depth in the level set 4 as in compared to the physics base. And this is important because the spread rate and the depth combined control the heat release rate, or they are indicators or measures of the heat release rate, which is important for plume rise and local heat flux. So those are the kinds of things we want to have a lower fidelity model reproduce. As I continue the simulations along, you see some blooming here. These are overstory, which is not shown. This is only the understory shown is in the green and the black. So you have some torching of trees. And then as I continue the simulations, these fire lines interact and then accelerate and leave the domain. So in general, what's happening is that where you have a head fire, you have greater consumption. And where you have a backfire, such as over here, you have less consumption. And that is reproduced in the level set. And as backfire leaves the domain, you can see it's starting to increase in size because now you have the ambient wind coming through, as Rod had mentioned. After all this is burned away, and increasing intensity of that fire. So these are showing the same on the left two plots show what you just saw in an animation. Now I have the time of arrival underneath the level set 4 result. And on the far right, we have the level set 5 result. The level set 5 model differs from the level set 4 in that the local, the head fire does not depend on the magnitude of the local wind, just on the direction, or the fire. Yeah, the head fire doesn't depend on the local wind magnitude. It's just constant. But the fire spread along the fire perimeter can change depending on whether it's in a flanking area or a backing area or a head fire area. And if you compare the TOAs, the time of arrival plots, and the consumption, you can see there's good agreement between these two models. You have head fire here on the LS5 between the first 2 ignition lines, the head fire spreading upwind in the upwind ambient direction, etc. The reason the LS5 model is of use is that because we don't depend on the resolving the local the local wind speed, and this is the horizontal wind speed, to determine the head fire spread rate, we can go to coarser grid scales, which speeds up the model, obviously. But I should say that this is not going to work in general. For instance, the fire spreading up a drainage will accelerate, and you can't capture that in this because you're assuming that head fire spread rate is constant. This is showing the overstory consumption. Again, on the far left is the physics base, and then on the right are the level set 4 and the level set 5. Overall, what's happening is that the physics base is showing more consumption, most likely due to its higher resolution than either of the 2 level set cases. But in general, the locations of the consumption are identified or consistent. When it does occur in the level set, it also occurs in the physics base, in other words. These are now time histories of the consumption of the understory here in the far left and the overstory on the right. The reason we have the difference here between the level set, which is shown in the symbols, versus the physics base, which is the solid lines, is that with the coarser grids, we're not capturing, we're filling more grid cells with vegetation, essentially. That's something we can fix. We just haven't done it yet. Overall, though, the time history agrees between the 2 types of models. Here with the overstory, we see initial agreement because you've got bigger trees, so we're resolving them more accurately. But there is a underprediction of the consumption in the level set. In particular, you can see here some trees torching, which are not captured. Here I have the heat release rate of the entire fire. And it's important in these scenarios that we're comparing here, the mass of the system is dominated by the grass fire. So the fire behavior and the heat release rate of the system is also dominated by the grass. And you can see that in this global heat release rate curve. The red solid line is the simulations you've been seeing, so everything is burning. This dashed black line is from simulations. Again, these are physics-based simulations in which we did not allow the overstory or the understory to burn. So the difference is the contribution of the raised vegetation. This kind of difference will not be of consequence to the smoke plume rise, however. And I'm showing down here in the right some more results of heat release rate, global heat release rate versus time. Of all the models you've seen so far, with the addition of level set 5 with the 2-meter resolution. So the smoke plume generated from these heat release rate kind of curves will be the same. So what this says is that if you're focusing on fire behavior, you need to have, by that I mean local consumption. Where's the consumption occurring? The fire line, this kind of stuff. Where is the overstory being consumed? Where is the understory being consumed? You need more resolution. If you are focused more on the smoke plume rise, you can get by with less resolution. We don't have time to show that kind of result, but that's what we've been finding.
About 2 minutes.
Thank you, Ryan. Regarding the costs, computational costs, the level set 4 with 25 CPUs, which you can use, which is capable, which high-end workstations are capable of at a resolution of 1 meter is 14 times faster than the physics-based, which did require 93 CPUs. So that had to be run on Amazon, or 29 times slower than real time. If we decrease the resolution to 2 meters, we decrease the computational time, and we end up at 2 times real time, or about 15 times faster than the 1 meter simulation. The last thing we wanted to show was a demonstration. This is now an FDS at a larger scale. It compares the 3 different models, level set models 1, 3, and 4. So 1 you've seen before, that's where we don't have any effect from the terrain, and there's no coupled fire atmosphere interaction. 3, we do simulate the wind going over and through the terrain, and if there was vegetation, through the vegetation. But again, we don't have coupled atmosphere interaction, and 4 you're familiar with already. So this is right here is the initial fire polygon. And this, the input file for this is created by what we call QGIS, which is online, freely available, as are these codes. So if we compare the final fire footprint between these models, you have this graph here. And with the fire atmosphere interaction, you see a larger footprint. And here we have that the fire area versus time. And again, when you include fire atmosphere interaction, you do have a faster growing fire essentially. Timings for this kind of simulation are shown here. This is with 13 CPUs, which is easily conducted on present day workstations. When you use the simplest model, it's essentially 10 times faster than real time. This simulation was over 2 hours, 2 hours simulated time. So when you move up to the higher, more computationally intensive simulations, level set 3, which again doesn't have coupled atmosphere interaction, but it does handle the influence of the terrain, it's 3 times slower than real time, and then level set 4 was 4 times slower than real time. So in summary, for surface fire behavior, for the scenario we've considered here, and obviously there's other scenarios to be considered, the 2 lower fidelity models that we showed did reproduce the coupled fire atmosphere behavior that was simulated by the physics-based, the highest fidelity model, with significant cost savings in computational time. And by fire behavior, we mean fire line interaction, the areas of the head, flank, and backing fires. And regarding the raised vegetation, we did have similar results in that the consumption rate and locations of the consumption in the understory were largely reproduced in the lower fidelity models. The overstory consumption was underpredicted, but the locations that were predicted in the lower fidelity models were also locations of consumption in the higher fidelity model. And then finally, with the terrain demonstration, we did show the relevance of the coupled fire atmosphere interaction in the overall fire growth. So that's it. Thank you.
Awesome. Thank you very much, Ruddy. It's a spectacular presentation, kind of on the range of opportunity space with coupled fire atmospheric behavior modeling, from high fidelity to low, and then some of the speeds. One of the questions in the chat, I think came up under Rod's, but because you illustrated this already, maybe you can address it while we exchange slides. Can these models incorporate crown fire? And since you are showing, torching and crown fire behavior, maybe you can address how they create transition from surface to crown fire.
Yeah. So because you've got the surface fire resolved, and you have, if you have grids that sufficiently resolve the raised vegetation, so that it's, you have some gaps in between the surface fire or surface fuel and the raised vegetation, and then also between the different types of raised vegetation, it all just comes along with everything else. You just simulate it all. The crucial thing is that you have the proper or sufficient spatial resolution to capture the gaps between trees, the gaps potentially within trees if those are important, and the gap, of course, between the surface fuel and the raised vegetation.
Great. Are there any other questions, either from co-panelists who can unmute their mic or in the chat? Ryan, I don't, looks like maybe there's one new reply, but I can't see it at the moment.
Let me see if I can get that for you.
Okay. And Ruddy and Rod will be here most of the morning and hopefully again for tomorrow's fire circle. If you have any questions, please feel free to directly message them in the chat or continue to ask the questions. We'll try to get to them. There's going to be another number of other presentations throughout the day. And if we don't quite cover those, then we'll make sure that we address them tomorrow in the fire circle. Since I am the next presenter, I will introduce myself. My name is Kevin Hiers. I'm wildland fire scientist at Tall Timbers Research Station. I've spent much of the last year detailed to USGS as a deputy wildland fire science coordinator out of the Reston office. But I'm here in the capacity as a Tall Timbers wildland fire scientist. And I will just say that for my talk, I have been fascinated. I was former fire program manager at Eglin Air Force Base and been fascinated since I saw Rodman Linn and Phil Cunningham produce some of the initial fire tech runs on prescribed, what really simulated prescribed fire conditions. And at Eglin, we burned over 100,000 acres a year. And for the first time as a manager who tried to, control fire and smoke in complex environments, I saw tools that actually added to the knowledge, base of what we needed. And so I'm thrilled to see how far tools in the tool suite like FDS have come over that period of time. And, one of the things that we've seen and increasingly asked is, are these tools right? How do you validate? How do you evaluate? And we all recognize that all models are wrong and some are useful. And unequivocally, I have found as a manager and now researcher, these tools to be exceptionally useful, not just in exploring, the physics of fire spread or coupling of fire atmospheric feedbacks, but as in this application space. But let's tackle for the next 20 minutes, the idea of validation and really reimagining what could be the case. So we're going to present on canonical evaluation scenarios for these kinds of tools as a potential way of increasing confidence and evaluating how they perform. Most of the studies to date, and y'all have seen some of these presented both in Rod and Ruddy's talks, have tried to link individual model performance against individual fires that have been studied in an experimental setting. Ruddy and Rod are not the only ones operating in this environment. There are a ton of other tools like Coffee and Warfest Fire that have used this individual fire performance. We did it most recently with the Gallagher paper in the Spring Hill reconstruction in New Jersey. This has been the standard method for evaluating the performance of these tools. And it's led to some skepticism. Are we tuning in? Are we just, making up the, inputs to make sure that the patterns match? And frankly, some skepticism is always warranted when evaluating this as we transition to operational applications. But the truth is that field data, even in these heavily studied, fires like FASME or ARC's Cadre, or even Fireflux in Texas, the field data rarely are good enough to actually even parameterize these models. We tend to focus on the fire, not on the initializing conditions like ambient wind field and turbulence. And this is even more true when we are under lighter wind conditions. And so most large scale experiments just simply don't have the initializing, the detailed initializing wind conditions to really truly serve as validation in the sense of that most people think of it like root mean square error. And so what we really need to focus on is maybe thinking of standard fires in a different way in order to really understand the capabilities and performance of these tools. And so some folks might say, well, we have standard fires. We got wind tunnel fires. But as this simulation from Ruddy provides using FDS, the wind tunnels themselves are not standard. And holding all things equal, the two fires above and below, all things equal, except for simply the dimensions of the wind tunnel, then we can see dramatic differences in fire spread and fire behavior. And so even what we tend to think of as wildland fire scientists, combustion scientists as being standard simply aren't, and lead to interesting coupled fire atmospheric feedback differences in, that these models can capture. And so the question becomes, how do you evaluate these tools? And we need to really think way beyond the idea of rate of spread. Rate of spread is certainly important in wildfire conditions, but these tools, as you've seen already in Ruddy and Rod's talks, go beyond that capability. And so we need to be thinking about how fire line interactions with the atmosphere produce predictable phenomena. I mean, as a fire manager, we know that fire is predictable in many conditions. Can we create these predictions with this tool suite, and maybe can we quantify the kinds of scenarios that managers are interested into a canon of opportunity? Ruddy and Rod have already done this with the Cheney plots from Australia. The long line, short line ignition is one of the most, I think, one of the best illustrations of how, just simply changing the dimensions of a fire line create feedbacks with the atmosphere that change the rate of spread. And both of them have shown how WFDS and FireTech and now Quickfire produced that phenomena. And now we're thinking about, instead of rate of spread being something that's inherent to a wind speed and a fuel load, now we're thinking about it as a function of the dimensions and fire atmospheric feedbacks. And so this lays a critical foundation for how we might want to move forward in validating coupled fire atmospheric behavior modeling tools. One other and a very important way has been done by James Furman, which is managers' opinion matters. We see a lot of fire, and James Furman reported managers overwhelmingly agreed that the CFD solutions for prescribed fire scenarios were in fact realistic and captured fire behavior that they expected from those situations. And that's really important for building confidence in these models. But it also shows that a phenomenological approach, these coupled fire atmospheric interactions that we expect as managers and as researchers, ought to be developed as a series of canonical tests for all existing tools, whether they're the high fidelity full physics models that Ruddy was showing, or the lower fidelity solutions that he walked us through with the level set. And then we want to specify, and document those ensemble performances of all the models against maybe the CFD solutions like Ruddy presented there as a potential way of gaining confidence in this. And so canonical tests are not new, obviously, and in the fluid dynamics world that Ruddy and Rod operate in, fluid dynamics canonical tests are well known, and some of the most famous would be the pool fires in a cylindrical chamber from Sandia, and then flow across a backward facing step, and the eddy that results. Unfortunately for us, wildland fire is not quite as well behaved as we saw with that wind tunnel. And so what would a canonical test case look like for coupled fire atmospheric behavior modeling? And because we can't get something like that backward facing step that's going to have a pure analytical solution, can we nominally capture the patterns and processes with these new tools and emerging tools in some sort of canonical test? And we think we can. We're going to spend a little bit of time exploring this. As I mentioned earlier, the Cheney plots from Australia really kind of set the stage and the first step towards this canon, and being able to compare fire spread of a single line of ignition, whether it's from long to short, and see if we can actually reproduce the differences in forward rate of spread is probably the simplest and best and most developed case of that would go into this canon. And as you reduce the length of line, you shorten it, the entrainment of cross flow into the flanks begins to inhibit the forward rate of spread of the head fire. And these dynamics are well known. They're reproduced quite well by the full physics or the high fidelity physics solutions that Ruddy and Rod have shown. And so this would definitely go into the canon. The other is one that we just saw Ruddy unpack with both a high and a low fidelity coupled fire atmospheric behavior modeling, is the interaction of a backing fire and a head fire. Over on the right is a study where WFDS has been used to reproduce this. And then in the middle, Rod and Francois Dupuis have done the same with FireTech. And that's me drawing what I think is this schematic approach to a head fire interacting with a back end fire. As Ruddy points out, at distances greater than 10 meters, the head fire reduces the ambient wind on that backing fire. And as it approaches, you should expect that backing fire to be drawn in and trained into the oncoming head fire. And we experience this on the fire line all the time. And so, again, something that a scenario that we feel like could be in this canonical test case scenario for a couple fire atmospheric modeling performance. Multiple fire line interactions. We've seen several of these already in the first two presentations. When you have multiple lines, this is a pretty typical ignition pattern for prescribed fire. Joe O'Brien has supplied this image here on the upper left of two head fires. As that upwind head fire spreads, it creates a buoyant plume and occludes oncoming wind from the downwind line of fire. That is not a backing fire up against a fuel break. It's actually, it was set as a head fire, and it is now, essentially stalled out by that upwind paired head fire. And so do our models actually create this multiple fire line interaction expected with upwind head fire and a downwind head fire interaction? Just like the head fire burning into a backing fire, we expect this downwind line to stall out, sit until that head fire from upwind begins to approach. And again, Ruddy, points out it's probably less than 10 meters, and then they'll converge, and that's exactly what happens. And so again, one of these canonical test cases that we feel like every couple fire atmospheric behavior model should be able to reproduce. Rod showed these earlier, and I'm going to go ahead and bring it up. Ring fires are a really interesting test case. We can set them as a continuous line of fire, or in the case of this performance of quick fire, Rod has set it as a ring of dot ignitions, and it creates a stall because there's a fresh air allowed to entrain in between this ring. But if we set it simultaneously, you should expect through the fire atmospheric interactions a convergence and an acceleration into the center under a no wind scenario. And you see that here in this case. And if we were to do this in the real world, it'd take a lot of igniters. And so let's think about it as a ring fire like we would typically set potentially in the field, which is a progressive ignition. And that then changes how that acceleration, how that heterogeneity of the fire comes together. And so again, ring fire scenarios should be included in this canon, because even under no wind scenarios or no wind conditions, that acceleration should be something that these couple fire atmospheric behavior models capture. One of the ones that's most important, I think, for us to also be able to evaluate model performance against is fire moving around obstructions. We tend to think about fire as being kind of a continuous line of head fire or backing fire, but most frequently we see in the field, fire is discontinuous. And how does a break in the fuel, in this case, Ruddy has used FDS to look at an oncoming head fire intersecting a square gap of fuel. How does that fire split, turn into two head fires, and then look at how the entrainment of wind around those two flanking fires modifies flow? As it moves past the obstruction, we get two flanks that are then drawn together, just as we've measured in the field. This is again Joe O'Brien from a paper we published in 2009, showing the same phenomena here. These fuel-free gaps are really important, and understanding how they create convergent zones on the back should be, again, something that a phenomena that these couple fire atmospheric behavior modeling tools can reproduce.
Kevin, about 2 minutes and no new questions.
Great. One of the things that these tools are also capable of is moving fire across obstructions, and how fire moves from one side of a road to another is actually pretty interesting. And Ruddy supplied one on the left and Rod on the right of two modeling tools that are performing this phenomena. But as you can see, we all test these tools under different kind of base conditions, 2 meters per second wind versus 5 meters per second wind. And having these canons specify the initializing conditions would allow us to compare, the performance of the models against one another. But a break in the road, or a break like a linear fire break like a road, is going to split up a head fire into multiple small ignitions, and this is a common occurrence when you sort of see fire move into these sort of obstructions. And do these models capture that fragmentation of line as a fire intersects a progressively wider break in fuel? I do want to point out that Dan Jimenez and Brett Butler, when he was in charge of the project, are funded to look at this out of the Missoula Fire Lab as a fire phenomenon. So we're going to have some really good empirical data to also back up these kind of canon. I think probably lastly, I'm going to leave you with the idea of large-scale phenomena, two large-scale phenomena that should fit into the canon, which is channeling of indrafts. Typically in the real world, we do have linear features that dominate flow patterns. And in this case, this is the International Crown Fire Experiment model with FireTech. And I want you to pay close attention to how fire or winds, ambient winds, are moving into the system. They're channelized, they're increase in speed, and then wrap around the unit. We get the same phenomena over here with a prescribed fire ignition around the corner of a unit. You can see that in-draft dynamic, that flow and channelization around roads produce when you have a strong updraft. One other large scale phenomena that we hope to be able to maybe include in the canon would be the development of crown streets when you do have fast moving crown fire. These features here in the middle, shown modeled through quickfire, are a product of variable wind speeds. And so in the canon, as we develop these canonical tests, we want to also think about variation in those environmental conditions and how that is reflected in the model performance. And so to quickly close, wind inputs in a canonical test case, if we develop these for a couple of fire atmospheric behavior models, allow us to specify those input conditions. It limits the error in poorly collected and really just hard to collect field data like ambient winds. The distance from the upwind model edge needs to be specified. How the boundary conditions each of these models influences fire behavior is still very important to be able to understand. And what we really want to start doing is reporting model performance in a very consistent way, since even some of these tools, as we change in scale, are not initialized the same way. And I think Ruddy already illustrated some of that. And so to start with, we're proposing smaller 1 hectare scale canonical tests, very similar to what I've shown here, and getting those specified initializing conditions rolling early on. I do want to return to the idea of empirical data. And because we've leveraged a lot of these well-studied experiments, but we don't have great initializing data, one thing we can do as part of this development of a canonical test case is to take all of these well-studied fires and then starting to specialize initializing conditions, so that we're all using the exact same inputs, or at least specific inputs that those models need well documented in order to evaluate performance against these empirical data sets of well-studied fires. And as Ruddy pointed out, deviation in model performance is actually important. We don't want the models to have the exact same answer as we compromise, say, fidelity for speed, but we want to understand how they vary in order to improve the models over time, and to understand where some tools may be more appropriate than others. I will end with the idea that this is not new. The advantage of a couple fire atmospheric model canon for validation is essentially a way of really increasing confidence in model performance and getting away from the older method of just thinking about error relative to a precise empirical observation. And getting into confidence is something that we see in hurricane model prediction all the time. When we see that cone of uncertainty, that is the ensemble result, not the actual, the probability that the hurricane is going to be there. And so developing the canon will help us design future modeling experiments to further validate and evaluate and improve these modeling tools. But it also just puts us all on the same page in terms of that confidence. And lastly, we also recognize that this tool suite covers a wide range of scales. And so some of these canon will not be appropriate for, say, weather or landscape scale modeling of coupled fire atmospheric feedbacks. And so we may want to be thinking about different canonical tests for those. I know we're out of time, Ryan, so I'm going to just quickly skip to any questions. If they're here, Rod or Ruddy, I'll chime in if I missed anything.
Kevin, no new questions. I think we can roll on over to Scott.
Okay. Scott, if you want to go ahead and begin to share your screen, that'd be great. Scott Goodrick, there he is. All right, so our next talk is going to be Dr. Scott Goodrick, U.S. Forest Service Southern Research Station, and he's going to be talking about smoke modeling as an inherent part of coupled fire atmospheric modeling tool suites. And you've seen a little bit of that with Ruddy's talk, but Scott's a research meteorologist who's been thinking about this for a long time with a variety of tools, and really thrilled that he's going to discuss this capability that's inherent in a lot of these coupled fire atmospheric modeling tools. Thanks, Scott. Take it away.
Thanks, Kevin. Am I all unmuted? All right. So I'm going to try to, one of the advantages of going a little bit later in the session is everybody's already talked about a lot of the advantages of the coupled fire modeling approach to the problem. But we're going to take a little bit of a different tact on it for right now, and focus on what this approach of coupled fire atmosphere modeling can do for us as far as for modeling smoke. You know, it was Ruddy touched on it a little bit as far as some of the heat release, but just kind of as a review for how we currently model smoke. You know, the process pretty much follows the pattern of estimating the consumption for the burn that we plan to do. From the consumption, we get the emissions and the heat release, and then we use a tool such as the Fire Emissions Prediction System, FEPS, to distribute those emissions in time. And then we take that information, plug it into a smoke model with some weather info, and we simulate our potential impacts. Now, that smoke model could be something as simple as a model like vSmoke, which is actually the one that I'll use for an example in this work, or something more complex such as high split or blue sky or day smoke, or a number of other potential models. Now, the problem that I see with this current process is at no point in here do we really get into where does our choice of ignition method come into play. You know, as the other talks have shown, you know, we've got all these different ways of igniting a fire. The fires are going to interact. That's going to change our rates of spread and consumption patterns. And this is completely neglected in the process so far. So this is an area where coupled fire atmosphere models can help by figuring out how these emissions and heat are going to be distributed in time by linking in our ignition method into the process. So again, I'll take advantage of being late here in the session and won't go into a lot of detail on this. But, you know, these coupled fire atmosphere models, depending on the level of fidelity, rely on concepts of conservation of mass, momentum, and energy, which allows us to figure out how a fire is going to behave. As Ruddy mentioned, with these three-dimensional models, you know, events such as crown fire are just a part of the process. It doesn't have to be a separate thing. How fire bridges gaps, or whether it bridges a gap, isn't a separate process. It's all governed by how we're transporting energy within the models. A couple of examples, you know, we've already kind of mentioned the whole, you know, suite of them, but FireTech, WFDS, WRF S-Fire, Quick Fire, coffee model. There's a ton of different tools that could be employed in this. For this example, I am going to be focusing on Quickfire, which is a tool that's been jointly developed by the Forest Service, Los Alamos National Lab, and Tall Timbers. That was really, from its outset designed for prescribed fires. And part of the intent was to be able to help inform these smoke models. So the basic setup that we're going to do for these studies is we're going to look at a simple 100-acre square plot. Fuel is just going to be grass, no overstory involved, keeping it very simple. The winds will be blowing from left to right across the screen. The winds are about 4.5 meters per second, or roughly 10 miles an hour, measured at a height of 10 meters above the ground. And our fuel moisture is initially set at 8%. So we're going to do a couple of different simulations. I'm going to kind of go old school and not have a bunch of animations. We've kind of seen that these models are great for producing nice animations, since they, three-dimensional, time-dependent models make great animations. But I'm normally a little gun shy about using animations in presentations, especially when I'm doing them online. Been bitten by that a couple times in the last 2 years of this virtual world. So we're going to kind of do this old school. Our first example is going to be a backing fire, probably about the least exciting example we can do. As I said, the wind is going to be coming from left to right across the plot. And for the backing fire, on the right-hand edge, we're going to have 2 igniters start in the middle and then proceed out towards the edge of the plot. And then the fire will just be allowed to back into the wind. Here we are at 100 seconds. We're kind of doing old school animation of just clicking through some slides. In 200 seconds, they've reached the edge, and we're going to not really show a lot of detail here. In 600 seconds, it's creeping along, and it'll eventually get all the way across the plot in about, I think, roughly about 3 hours. It'll take it to get all the way across. So this was probably the least interesting example that could possibly be done. But what it is going to do is kind of provide one end of the spectrum of probably the lowest emission rate and lowest heat release rate that we could get. And we'll contrast that with, somebody's already kind of shown a ring fire, kind of in a modification of one of the ones that Kevin showed earlier. We're going to have igniters start at each of the corners and then move towards the center of their respective side. And as you can expect, we've still got our wind blowing. So this is not a ring fire in zero wind, as you can see by the differences from the upwind edge of how quickly it's moving. But you can see that, we get quite different behavior. And as we start to close off and finally close off the ring, the behavior picks up quite dramatically. We start getting the fire lines interacting. And within our 600 seconds, the previous backing fire had creeped just a little bit into the plot. The ring fire is basically about done. Within a few more seconds, it'll finish off that last little bit of fuel. And we will be completed with that. Now, those are just 2 of the, like I said, kind of defining the spectrum on this. There are other ignition patterns that we could be looking at. We could be doing an aerial ignition, having a helicopter moving across, dropping ping pong balls. Chevron, where we're having some lines of fire drawn up into the wind to create a different pattern. Flanking fires, lighting up the sides and then closing it off at the head. Doing just a straight head fire ignition. Spot ignitions by hand or strip heads was one that's been shown, and a couple of other ones. So there are a range of options that could be explored in this. And if we take our two cases that we looked at first, this is kind of that envelope that I was mentioning. So we're looking at a 20-minute time frame and how the fuel was consumed. Down along the bottom, the orange line, you can kind of see the backing fire, just, a slow, constant creep into the wind. It'll eventually get up to that 100%, but it's going to take you a long time. The ring fire quickly ramps up, and within a short amount of time has pretty much consumed all the fuel. Now, if we add in a couple of other of those possibilities, we'll look at the head fire, this one here in the middle. We started off the head fire by igniting the backing fire because, in general, we wouldn't send a head fire racing towards a line that we haven't secured with a black. And so you can kind of see that at the beginning, both the back and flank and head fire are all pretty analogous, as it's basically the ignition of the backing line. And then after that is complete, we started the head fire from the center point of the plot and expanded it outward. And you see that it rapidly burned out the entire unit, but it did it slower than the ring fire. And this is those fire atmosphere interactions. Those interactions lead to stronger winds influencing the fire than what you get from the environment alone. So you get quite an advantage with some of these other patterns that can include fire atmosphere interactions, where we have multiple lines of fire interacting. Now, the flanking fire, the other example here that kind of is, filling in some of the center part of this envelope. Again, it starts off very much like the backing fire, and then we start dragging fire up the flanks, and probably right around 12 minutes or so into the simulation, we've ignited all the way the flanks along the whole side, and we begin closing in the head. And that's when we get the dramatic acceleration in the fuel consumed. Now, if we add in the other possible ignition methods, you can kind of see that they all fall within this envelope that's set by the ring fire and the backing fire. And one of the interesting things is we start adding in ignition methods such as chevron or the strip fire or the spot ignition. Those are ones where we have a lot of flexibility in how we do them on the landscape. How many different strips are we igniting? What's the spacing between spots? Those are going to move their respective lines within this envelope and change exactly what that rate of fuel consumption, or analogously your emissions rate, looks like, as you're kind of controlling how much fire is in the backing, flanking, or head fire categories. That's what you're manipulating with your, controlling your spacing of your strips and spots. So you can kind of see that this captures a lot of that range of behavior. And if we move it over into the world of, energy release that would drive the plume, so this was kind of the emissions piece. If we look at the energy release, you can see, again, kind of defining our envelope here. The backing fire doesn't release a lot of energy into the atmosphere, isn't going to drive a very significant plume, but the ring fire is going to, generate a very strong convective plume over a short amount of time. And as we add in the other possible venues here for the energy release to the atmosphere, what you're basically seeing is kind of a blurring out, a smearing of the amount of energy over more time with some of the different ignition methods. So
Scott, about 2 minutes.
Perfect. So we've got a lot of variability here. So we're still keeping fairly strong convective plumes, but we're spreading them out through time. It's the same amount of energy being released, since we did a simple grass fire where eventually everything gets consumed in this case. it's the same amount of energy just spread out through different periods of time. So we'd get eventually some different plume models. Now, as Ruddy pointed out, there might not be a large difference between, say, the ring fire, and in this case, the chevron pattern, or the strip head fire. But if you looked at what the head fire was doing, it's delayed it out through a longer period of time. The peak is considerably lower. It would generate a different plume. Now, to take this, so basically this is accomplished kind of what we do with FEPS to do those first pieces of the process of looking at the consumption and then emissions and then spreading it out through time. That's now done naturally as an extension of using the coupled fire atmosphere tools to model your fire. And so now we can start looking at how this would feed into a simple smoke model such as V-smoke. Well, V-smoke has this one little input parameter defined as the plume rise fraction, which for most applications is set at about 0.75. So you can see that if you set it at a value of 1, you get figure A at the top, which is pretty much all the smoke is in the convective column and subject to plume rise. If you put it between 0 and 1, you get some mixture of ground smoke, which that ground smoke would be very analogous to what we would expect from that backing fire, which had very low energy input. And you could kind of see here in figure B that kind of defines the envelope of what we were looking at from our different cases. So if we look at what the difference between doing, say, a 0.9 in that plume factor versus, say, a 0.1, to look at those two different extremes that were our envelope. So this is the high. We put our fire up here in the upper left-hand corner, and this is with the plume rise fraction set to 0.9. You can see we still get significant smoke on the ground, but the highest concentrations are all right near the fire. The plume is lifting vertically, and what's getting down to the ground is mixed down by the boundary layer circulations. And so you're basically mixing smoke downward to the surface rather than trying to mix it away from the surface. The convective lift is keeping all the smoke within the plume and lifting it up. If we go to the other end of that envelope, where we're having plume rise fraction of 0.1, and we're more in that backing range, you see that we get higher concentrations near the ground as we're dragging that smoke all along the surface, and then waiting for the boundary layer processes to mix it up away from the surface. Now, in this case, this was assuming the same emission rate for the two fires. Naturally, that wouldn't be the case, but this was just to emphasize the role of that plume rise fraction in what these differences in how we ignite can produce in the plumes. So where this is kind of going, this very preliminary stuff is showing that, yeah, how we ignite the fire is an important piece of how the smoke dispersion should occur. We didn't even get into how the distribution of that heat release and consumption in space and time influences plume development and structure. That was a little bit beyond the scope and for another talk. But one of the other places where we're going is, what about integrating dispersion modeling into the coupled fire atmosphere tool suite? We've already got a three-dimensional atmosphere that we're working with. We've got the heat release going in and driving convective plumes. There's already tools available with the quick atmospheric modeling suite for including plume dispersion. So I think we're poised to go to a more integrated approach to modeling prescribed fires and smoke impacts. And that's kind of where some of our work is heading. And we'll stop there.
Awesome. Thanks Thank you, Scott. I really appreciate it. It seems like there's a little bit of delay in when we're getting some of the questions, but again, if anybody on the panel has any questions for Scott, feel free to jump on in. There is one question in the chat for Ruddy. Ruddy, if you have a chance to go into Wahova and take a look at that. Carrie Ann asked how smoldering's handled in the FDS tool suite and some of the advantages there.
Okay, will do.
Okay. So if there are no other questions, then Justin, you can go ahead and start sharing your screen. We'll go ahead and move on to the last talk for this morning's part of the special session, and we'll pick it back up after lunch. But Justin Ziegler, who's a doctoral candidate and research associate at Colorado State University, is going to talk about using advanced modeling tools to further fuel hazard reduction and restoration treatments. And it's going to be a huge topic, obviously, moving forward with the recently passed infrastructure bill. Justin, appreciate your participation, and I got your slide, and I'm assuming that you're unmuted. Take it away.
All right, thank you, Kevin. So today I'm going to talk about some work that I've been pursuing with Chad Hoffman, Russ Parsons, Jim Manakis, and Morris Johnson. We've been exploring the use of coupled fire atmospheric models as a virtual laboratory to examine the effects of fuel treatments from individual tree to stand to landscape scales. So if we recall, the simplest ideas behind fuel hazard reduction, the first principles, reason that we should reduce surface fuel load, increase height to live crown, and decrease crown density. Put into action into silvicultural planning. And I've heard this verbatim yesterday, in fact. This typically means separating the tree crowns and thinning from below. So if you could see in these two photos here, on the left is a pre-treated stand and the right is post-treatment. We can see a vast simplification of the forest structure. This really contrasts against forest restoration. I think Scott Stevens recently and others put this well. So if we see in this image up top that we have the traditional fuel hazard reduction scheme in number 2 of this polygon, and that's really different from number 1, which is an exemplar of forest restoration, where we have groups of trees interspersed with openings. So the arrangement of trees vertically and horizontally really differs. And the implications for this possibly on fire behavior are not lost on anyone in the literature. We see a lot of hints at potential liabilities or trade-offs that are introduced when we aim for forest restoration over fuels reduction in regards to fire behavior and effects. So from what I can gather, trying to answer the question of whether or not there's a significant trade-off, look at the literature. We know that generically, fuels treatments are effective at reducing fire behavior across a whole slew of different prescriptions. And work from our team in the past showed that restoration treatments are effective at reducing fire behavior. Though this study didn't have a counterfactual where we tested against traditional fuels hazard reductions. Russ Parsons and others, their work using WFDS really hinted at maybe effectiveness of fuels treatments or restoration treatments is really dictated by just the amount of gross fuel load in the canopy and surface strata. Not so much by the arrangement of fuels, but interestingly, they found that fuel heterogeneity really increased the variance of fire behavior, especially locally. And this might be because that fire behavior can increase locally where you have pockets of higher fuels. So this could be thought of as group torching. So I thought maybe I could actually break down this question, since no one has explicitly compared different schema of fuel treatment designs against each other into a more methodical framework. So this study that we did breaks down our questions into sub-questions. So are Are we creating more treatment effectiveness when we reduce the vertical variability of residual trees? So that's hinting at the thinning from below component. Or when we reduce the horizontal variability of residual trees. So that's getting at the groups of trees versus separation of tree crowns. And given that wildfires occur across a vast range of forest structures with different ambient conditions occurring in the fire environment, we wanted to be able to place the effects of the fuel arrangement in relation to the other general questions about like how much are we cutting, how much fuel is available, and how do the arrangement of fuels matter when we're talking about the wide array of burning conditions that might be present. To accomplish this, we set up a slew of levels for each of these components that might be influencing fire behavior, and we simulated these in WFDS, the Wildland Urban Interface Fire Dynamics Simulator. And in this study, we're using the full fidelity physics-based variant that Ruddy was discussing. And thankfully, all of these levels of all of these factors would have created a large number of simulations had we done full factorial, but we used a de-optimized design, which cut down on a number of simulations to 124, including pre-treatment and post-treatment. And you can see here, we have 3 different levels of residual basal area from 5 to 10 to 15 square meters per hectare. And keep in mind, I'll show on the next slide where we're simulating these studies that might sound really small if you're, say, in the Pacific Northwest. We have 3 different wind speeds that are typical in wildfire scenarios, 3 different medians for the surface fuel load. These surface fuel loads will vary spatially, and they also have accompanying surface fuel moistures of 5, 8, or 11%. And I'll get into the cutting methods in 2 slides. So we conditioned these experiments on actual stands to try to reproduce more expected results. These are drawn from some data that we've made open. We have a site in Arizona and 4 in Colorado. There were 7 sites that we had mapped to 4 hectares, but only 5 of these had a large enough stocking for us to thin from. So they all are ponderosa pine dominated and had an initial stocking of at least 20 square meters per hectare basal area. Here's one of the example sites for a given basal area, in this case, 10 square meters per hectare. Briefly, of these 3 different horizontal arrangements that include thinning from below and without thinning from below, we could see an illustration of the effects of our prescriptions. So random thinnings, of course, were just an unweighted sampling of trees that we removed successively until we reached the desired basal area. Thinning from below, just like an FVS, would have just culled the smallest trees on up until we hit the requisite basal area. If there was a spacing-based prescription, we just removed the trees that were nearest to another tree. And if we combine that with the thinning from below, then we first removed, we removed half of the trees to be removed first by thinning from below, taking out the smallest trees, and then we implemented the spacing-based scheme. With variable retention harvest, which more closely resembles restoration style treatment, we did a tree group retention and then we punched in holes. So this tree group retention is based loosely on the idea of the ICO individual clumps and openings scheme, where we have tree groups, which are chains of trees that are within a certain distance of another tree within the group, here 4 meters. And then after we took away trees that weren't part of a group, then we punched in holes to meet our basal area goal. And again, if we had combined it with thinning from below, first we took out half of the BA through small tree removal, and then we implemented the variable retention. For our analysis, we looked at rate of spread and canopy consumption as predicted by WFDS. And we put in each of our independent variables, that is the basal area, surface fuel load, surface fuel moisture, the ambient wind speed, as well as interactions to examine the differences between the treatment schemes. So we have the horizontal arrangement and with or without thinning from below, and the interaction with basal area to test whether or not the differences between treatments depended on how much we had removed. So as we could have expected, rate of spread was largely driven by surface fuel moisture and wind speed, and canopy consumption was driven by basal area, surface fuel load, and surface fuel moisture. So I'll present the results to test our deriving questions using a panel of 3 plots, and these are the marginal effects first among the different cutting methods. So we'll look at horizontal arrangement by thinning from below, and then we'll look at horizontal arrangement conditioned on basal area, and last, whether or not we thin from below conditioned on basal area. First, we'll look at rate of spread. And I'll use some animations here just to zero our eyes in. What we see on the left is that when we don't have a thinning from below component, the spacing-based thinnings had a slightly lower rate of spread than the variable retention. But once we add in a thinning from below component, the rates of spread are brought to parity. So thinning from below slightly increased the rate of spread, which was commensurate with the rise in within canopy wind speeds. Then when we look at the differences between the horizontal arrangements contingent on the residual basal area, we see that as we cut more, the differences between the horizontal schemes are expressed to a greater degree. So as we cut more, we see that the spacing-based thinnings and just a random cutting perform just the spacing-based thinnings decrease at a faster rate as we cut more versus random or the variable retention. And similarly, as we cut more, we see the effect attributed to thinning from below gets emphasized to a greater degree. So as we cut more, our thinning from below is going to have a higher rate of spread than without thinning from below. The results from canopy consumption are fairly similar with one difference. So we'll go through these. Again, we see that the variable retention harvests have a higher canopy consumption than spacing based. About 5% of the canopy consumed, that's the delta. But again, once we add thinning from below with them, they're brought to parity. When we cut more basal area, the canopy consumption decreases, but again, at different rates depending on how we arrange the residual trees. So again, the variable retention harvest scheme has a higher canopy consumption than random or spacing based. And here, when we thin from below, again, the effect of thinning from below gets expressed to a greater degree as we cut more. And we see that thinning from below substantially decreases the canopy consumption from about 45% to call it 30% canopy consumption. So to answer our last question, how much does the silvicultural tactics matter in context of the overall burning environment that we might expect in a wildfire? To examine this, I plotted the effect size from each of these independent variables in our regression. And to try to zero in on what's effectual versus ineffectual, I use a textbook definition or breakpoint of 15%. And that's these green highlighted bars. So when it comes to rate of spread, really everything is driven by wind speed and surface fuel moisture. So any silvicultural tactics tend not to have any influence at all.
Justin, about 2 minutes.
Thank you. And with canopy consumption, only thinning from below and basal area pop out, aside from the environmental conditions like fuel load and fuel moisture. So my main takeaway for this is that really the concerns about how we leave trees is not as important as how many trees we leave. So and this is really illustrated in this figure here the fact that we just cut is going to reduce canopy consumptions, and we might have minor differences depending on where we leave the trees. But again, if we add in a thinning from below component, this really diminishes any differences when it comes to the horizontal arrangement. So I think whether you use conventional hazard reduction treatments or restoration treatments, you're going to see an effect. Maybe the only context when you might really want to optimize for reduction of fire behavior might be in the WUI, but otherwise, I think there are a lot of things that we need to consider and a lot of goals that we have in regards to these treatments. And so this opportunity cost is so small that I think it can be considered a non-issue, at least in the wildfire environment. So to wrap up this study, I just want to condition the outcomes on the burning environment just to ask whether or not differences between treatment methods magnify or diminish under more or less severe fire weather. I will note that as Rod had said, marginal fires, that is, for example, in the prescribed fire realm, they're probably driven a lot more by fuel heterogeneity. And that's, these, here we're burning right below or around the transitory point where we might have some torching or conversion to crown fire from the surface fire. So I think further studies should maybe look at the range of burning conditions within the realm of prescribed fires, because I think their arrangement might have a larger influence. So with that, I'll leave you with one of these illustrations of the simulations. And if you have any questions, feel free to drop them for me. Thank you.
Thanks, Justin. That was fantastic. Really appreciate that. There is one question already in the chat or the Q&A. It's from Seth Bigelow, and it says, Justin, presumably there'll be an interaction between pattern of thinning and surface fuel moisture, i.e. drier fuels and heterogeneous thinnings maybe. Could this affect your conclusion?
I think my guess would be, I will note that I didn't vary surface fuel moisture spatially. My thought would be that in the wildfire conditions, the difference between 5 or 7% fuel moisture in an opening versus under a tree, that might be so far outside of the range, the Goldilocks zone where it might matter. And again, I think that this question will be more pertinent for the prescribed fire environment than wildfire weather.
I think one of the really neat things, though, is that you could, in fact, simulate that, right? I mean, it's not, even if you expected that, that's one of the sort of the attributes of these modeling tools is that, you can start to really unpack variation as a theme, not an annoyance.
Yeah, and since I have a couple of minutes, I'll just add, I think it's been great talking or listening to all of these talks. And I think that this study shows maybe a new way to use these models. So we can look at case for case simulations, and maybe we can try to validate or replicate prior fires and maybe tweak the conditions to look at counterfactuals, or we can look at canonical simulations to try to elucidate phenomena of interest. But these large batch simulations might help us understand generalities that we can pull and separate the signal from the noise that we might not see when we look at case studies.
Agree. Just one more quick check, and Ruddy, I don't know if you had a chance to look in the Huba chat, but if you want to jump on, Kara says, nice presentation. Ruddy, can you tell us a bit about how smoldering is handled in the physics-based versus the LS, the level set simulations? And are there drawbacks when using level set to address any of the smoldering at or behind the flaming front?
Yeah, okay. Thanks for the question. Right now, there's not smoldering in the level set. It can be in the physics-based. The issue with smoldering is that right now, the models that are used for that, at least in FTS, WFTS, require what's called an Arrhenius kinetics scheme, which also requires that you have sufficient resolution to get the temperatures of the solid right and the heat fluxes right. So as you go to these coarser grid scales, that becomes very problematic. But this isn't to say that again, based on the physics-based results or other maybe observations and measurements, we could incorporate smoldering. It just hasn't been done yet in the level set.
Awesome. Thank you very much. We are coming up to the end of the morning session. I want to extend my appreciation and thanks to all the speakers and all of you participating. We will return in the afternoon. I think maybe 20 minutes. Ryan will set us straight here in just a second for logistics of that. But thanks again to everybody. And Ryan, do you have some final housekeeping for us?
Kevin, thank you. Appreciate that. Thank you to all of our speakers for sharing your expertise with us today. This session will be available in Whova, our conference app, within 2 weeks after the conference ends. Up next, we have a 20-minute break before our next round of breakout sessions. Choose from our second virtual field trip, 5 special sessions, and 1 general session. To choose the one you'd like to join, use the Agenda tab to the left of your screen and click Sessions, and click the main session title to join. To join the session offering Spanish and Portuguese interpretation, be sure to select the session titled Ecosystem Services. Thanks again to all our speakers. Take care.